Welcome back, everyone. Let's go ahead and use PyTorch to implement a simple linear regression. Then, in the next series of lectures, we'll expand on this general idea to build out a simple neural network. Then after that, we'll see a full artificial neural network model on tabular data that contains both continuous and categorical variables. But let's start off with just performing a simple linear regression. I'm going to head over to the Jupyter Notebook. Okay, here I am in my notebook. I'm going to, as we have been doing, import torch, and I'll also be importing numpy as np, and since we may be doing a little bit of plotting, we'll say import matplotlib.pyplot as plt, and then just in case you're using a different version of Jupyter Notebook, you can say matplotlib inline, and this is only for the notebook. It's a magic command to see the actual visualizations in this notebook. The most recent version of Jupyter Notebook shouldn't need this inline command. And if you're running these things as a script, then inline is not necessary for you. You can just not have this command at all. Okay. The other thing we're going to be doing, and we'll be seeing this a lot later on in the course, is I'm going to import torch.nn as nn. That way I don't need to keep writing torch.nn all the time. So a lot of our neural network functions are going to come from torch.nn. Okay. So the first thing we want to do after performing our standard imports is to create a column matrix of x values. We can create tensors right away rather than convert from numpy arrays. So I'm just going to say x. Note my capital X notation. That matches up with the typical mathematical notation you'll see here. We'll say torch.linspace, and linspace is linearly spaced elements. We'll go from 1 to 50, and we'll ask for 50 linearly spaced elements starting from 1 all the way to 50. And then what I'm also going to do is reshape this to be -1 by 1. So if I take a look at x, I have this tensor. So this -1 by 1 allows it to just be this kind of column of values. So note the dimensions here. Okay, so I have 1, 2, 3, and then we go all the way to 50 because I was using linspace. So there's my x values. Next, what I want to do after I have this column matrix of x values is create a random array of error values. So I'm going to have a little bit of noise here. What we're going to do is to make sure you get the same random values I do, let's go ahead and set the same seed. So I'm just going to choose 71. Again, it's an arbitrary choice, but make sure you match this and make sure in the same cell you go ahead and make your noise or error values. So we'll say torch, random integer, and we'll say from -8 to 9. So recall, if you do shift tab here, that's our low and that's our high. And what we're going to do is have it be the same size as what we just created, which is 50 rows by 1 column. And last thing I'm going to do is I'm going to specify this data type to be converted into float. So since these are integer values, I actually want them to be float, which is what we have right here. That's why there's a dot there. So let's go ahead and let those error terms also be floats by specifying that data type. And then I'm going to go ahead and show you those random numbers. Okay, what we're going to do now is actually set up our column matrix of y values. So we're going to set up our equation for y equals mx plus b. So we'll say our formula is y is equal to, and we'll say 2 times x plus 1. And to make sure this isn't a perfect line, we'll go ahead and add in those error terms. So that's the noise that we can't really account for. So if we just had 2x plus 1, then the points would essentially just be a perfect straight line. With this error term, we'll see a little bit of noise there. So go ahead and run that. And then if we check the shape of y, we see, again, it's 50 rows or 50 values just in a single column. Let's go ahead now and plot out x versus y. In order to actually plot this out with matplotlib, we can't actually plot out a PyTorch tensor, so we'll need to convert these back to numpy arrays in order to plot them out. And you can do that by simply saying the tensor.numpy as a method call, and it reports it back instead of a tensor as a numpy array. And the reason we'll do this is simply for plotting purposes. So let's go ahead and make a scatter plot. We'll say plt scatter, and we'll plot the x points versus the y points. So when you run that scatter plot, we get x versus y here, and note that there's a little bit of noise, but the general formula is still 2x plus 1, so our slope is 2, and our y-intercept is 1, and then there's a little bit of noise here. And what we want to do is we want to be able to use PyTorch and fit a simple linear regression line here. So note that when we created tensor x, we did not pass requires underscore grad or gradient is equal to true. This means that right now, this y doesn't have a gradient function, and so y dot backward won't actually work. Since PyTorch is not tracking operations, it doesn't actually know the relationship between the variable y and x. So keep that in mind. This is just a simple linear model right now. We're not keeping track of any gradients so far. Okay, so let's go ahead and build out this simple linear model. So what we're going to do as a quick demonstration, we'll show you how the actual built-in neural network.linear model pre-selects weight and bias values at random. So what I'm going to do is I will set a seed here. We'll say manual seed. And again, the reason I'm resetting the seed is just in case you run these cells multiple times or run the values multiple times. It's really important that for you to have the exact same values I do, you do everything in the same cell the way I'm doing it. I'm going to choose just 59. Again, essentially these values are arbitrary, but I want you to choose the same ones. That way you get the exact same noise profile that I do. And we'll say model is equal to NN, and then we're going to create a linear model. And the linear model takes in the number of features in and the number of features out. So you can notice here that it supplies a linear transformation to incoming data, and there's our formula. Y is equal to mx plus b, or at least some sort of format up there. This is A transformed, but we'll talk about that later on. Right now, the n number of features we have is essentially just x. And then the out features, well, that's just y. So we'll say in features is 1, out features, and make sure this is with an s there, is 1 as well. And then what I'm going to do is I'm going to go ahead and print out the model weight. Make sure there's a L at the end of that. And then I'm also going to print out the model bias. So run that, and if you set the same torch manual seed that I just did in this same cell, you should get the same weight and bias values, which are technically random. And notice right now that automatically we are now connecting this and requiring the gradient. So we have 0.106 as our first random weight value, and then our first random bias value is 0.96. Now PyTorch lets us define models as object classes that can store multiple model layers. And in upcoming sections, we're going to set up several neural network layers and determine how each layer should perform its forward pass to the next layer. For right now, since this is a simple linear model, we actually just need a single linear layer. And so what we're going to do now is we're going to set up our model class. And this is the sort of syntax we're going to be using throughout the course. So we set up a class variable called model, and this is going to inherit from nn.module. And there's two main methods. The first one is our instantiation method, which recall as underscore underscore init underscore underscore. This takes in the self parameter, takes in n features in, and then how many features out. And what we're going to do here is we'll call super dot underscore underscore init underscore underscore, and then self dot linear is equal to nn, a linear model that takes in n features and out features. So this is essentially what we were building up out here, but now we're putting it within this class call. So we instantiate with this linear layer, just a single linear layer, and then the method we're going to provide here is the forward method, which takes self and x, and we're going to say that the y predicted values is equal to this linear layer when we pass x through it. And then we're going to return the y predicted values. So let's actually quickly go over what's going on here in this class model, and then in part 2 of this lecture series, we'll go ahead and show you how you can use this newly created model class. So one thing I want to point out here is that this linear model layer here doesn't actually really refer to linear regression. Instead, it's truly describing the type of neural network layer that is employed here, and that's a linear layer. And a linear layer is a fully connected or dense layer. And going forward, our models may contain linear layers, convolutional layers, pooling layers, etc. This is actually a specific layer type. Now, when the model is instantiated, what we're going to need to do is we're going to need to pass in the size or dimensions of the incoming features and of the outgoing features. And for this purposes, we essentially just have x and y. We have one single x value, and we're trying to predict what the y value should be. So we're going to have one incoming feature and one outgoing feature. But later on, we're going to expand this idea to more complicated networks where we have many features, such as many incoming features of x, and maybe we're only trying to predict one outward feature, like the price of a house. So you can imagine there's many in features of a house, like the size of the house, maybe the age of the house, the number of bedrooms of the house, and then the out feature will just be one, which is the price of the house. Okay, but for classification, you can imagine something like trying to predict the category or neighborhood a house belongs in. We could have one out feature per category. Errors there, and what we're going to do is we're going to continue in part 2 to actually show you how you can use this model. I'll see you there.